Hi everyone online. Thank you for being here with us today. We have with us Dr. Jinghui Chen. He's the postdoctoral fellow at both York University and University Journal.
Yeah.
And we look forward to your talk.
Okay. Hello everyone. First of all, welcome to my presentation. And also thank you for Professor Berman and Dr. Janani for the invitation. My name is Jinghui Chen, and I am a joint postdoc at the University of Toronto and York. And oh no, it works, but we cannot see the point in here.
You can use the
it's really the mouse the trade. You can use the mouse as a pointer.
Okay. Okay, it's fine. And I'm a joint postdoc at the University of Toronto and York University. And today's talk is about a question: is there a link between correlation and coskewness? This topic is related to two of my working papers. The first one is the modeling coskewness with zero correlation and correlation with zero coskewness. The second is bounds of coskewness in portfolio choice. And both are co-authored with my PhD supervisors, Carol Bernard and Stephen Manu. The presentation is divided into 5 sections. We mainly focus on the second, correlation and coskewness with no marginalness. At third, wrong correlation and wrong coskewness. And fourth, correlation and two-dimensional coskewness. Okay, let's move to the first section, introduction. From the title of this presentation, it is clear that we are going to study the relationship between the correlation and coskewness. And first to know is what are the correlation and coskewness. But I think everyone is familiar with the concept of a correlation coefficient, especially for the Pearson correlation in here. And in figure 1, we can see that there are different Pearson correlations to describe the different dependent structures between x1 and x2 in here. And the formula of the Pearson correlation is this one, where mu I and sigma I are the mean and standard deviation of the random variable xi respectively. However, the coskewness is a less well-known concept compared with the correlation in here. Let's review the definition of the coskewness. The coskewness of random variables x1, x2, and x3 is in equation 1 in here, and it is a statistic definition for the coskewness. We will introduce another type of coskewness in the following section. At first glance, we may think that the coskewness in here is only a one-dimensional extension of the correlation in here. Moreover, here is a table from the literature. We can see that the correlation in this line and the coskewness in these two lines, the coskewness is either decreasing in terms of the correlation or increasing in terms of the correlation. Thus, it may exist some relationships between the correlation and the coskewness. However, I use some propositions and examples in the following sections to prove that in general, there is no relationship between the correlation and coskewness. The second section deals with assumption of the normal marginalness in here. So what we talk in here is that the marginal distributions are normal. It's symmetric. The property is symmetric. And in this section, we prove these two propositions. First, for any given value of coskewness, in the range between the minimum and the maximum values that are admissible for the given marginal distributions, there exists a dependence model such that the coskewness among the three variables attains this value. In contrast, the pairwise correlations are all equal to 0. And the second is for every given set of correlations among the three variables, there exists a dependence model such that their coskewness is equal to 0. But we can get any correlations, and if it's admissible, the same. Okay. Here in this subsection, we prove the first proposition in here. Recall the theory 3.1 and 3.2 from my first paper, coskewness and dependence uncertainty. We can have this lemma. And the main assumption is that Fi are symmetric. Then the lower bound of the coskewness of x1, x2, and x3 is minus this term, the expectation of the product of these three terms. And the upper bound of the coskewness is equal to expectation of the product of this term, in which Gi, that is G1, G2, G3, is the distribution function of the absolute values of normalized Xi. Then we know that's the maximum, we proved that the maximum coskewness is attained by the copula of the random vector U1, U2, U3 in here. The minimum coskewness is attained by the copula of U1, U2, U3 in these expressions. Figure 2 shows the support of copulas that maximize and minimize the coskewness for the symmetric marginals. That is, we show the plot of these expressions and these expressions. The left panel is the plot for the maximizing case, and the right panel is the plot for the minimizing case. Then we can define the mixture copula in here. Similar assumption on the symmetric marginals. One point to highlight is that we define a Bernoulli random variable in here, B, with parameter lambda. Then the dependence structure of x1, x2, and x3 is called a mixture copula. When the chain variant random vector, when xu1, u2, u3 are in here, actually the chain variant random vector u1, u2, u3 lambda is a kind of linear combination between the chain variant random vector from the maximizing copula in here and the minimizing copula in here. So because u1, u2 and u1, u2 in both the maximizing and minimizing copula are the same, the only difference is the u3. They have different structure. In figure 3, we show the effect of the parameter from the Bernoulli random variable on coskewness by using the Monte Carlo simulation. We can see that the coskewness in this y line, the change of the coskewness in terms of this parameter lambda in here, when lambda equal to 0, the coskewness is minimized, and when lambda equal to 1, the coskewness is maximized. And these two values in here are the theoretical lower and upper bounds of the coskewness for the normal marginal distributions that we proved in our first paper. Finally, we come to the proposition. Let x1, x2, x3 be a chain variant random vector with normal marginals and the mixture copula C lambda. We use the symmetric property of the normal marginals to prove that the pairwise correlation coefficients of the three variables are equal to 0. where their coskewness takes any arbitrary values depending on the value of lambda in the range of minimum and maximum coskewness. This proposition proves the first proposition that we propose in here, and in the next subsection, we build a dependence model to prove this second proposition. Here it is, and we use the trivariant Gaussian random vector to illustrate that the coskewness of x1, x2, and x3 equals 0 for any possible values of the correlation rho ij of these two random variables xi and xj. In here, we can see that means the correlation coefficient can be any admissible match in the admissible values in here, but we always can get a 0 coskewness in here when we have a trivariant Gaussian random vector. Okay, in section 3, we generalize our result by using the wrong correlation and the wrong coskewness. Here are the definitions for the wrong coskewness and the wrong correlation. The standardized wrong coskewness of x1, x2, and x3 is defined as Rs x1, x2, and x3 equal to this. This definition is also from my first paper. And the wrong correlation or the Spearman's correlation of x1 and x2 is defined as this one. Similarly, we also prove two propositions in this section. First, for any value in -1 and 1, one can construct a dependence model such that the standardized wrong coskewness among x1, x2, and x3 has that value. In contrast, the pairwise wrong correlations among them are equal to 0. Second, there exists a dependence model such that the pairwise wrong correlations and can take any possible values in -1 and 1, but their standardized wrong coskewness is 0. Instead of using normal marginal distributions in section 2, in both propositions, we have the marginal distributions Fi to be any strictly increasing and continuous marginal distributions. Okay, then we use the model of the mixture copula C lambda again, but the strictly increasing and continuous marginal distributions Fi. We show that the standardized wrong coskewness can take any possible values in -1 and 1, while the wrong correlation coefficients are all equal to 0. This proposition proves the first proposition we mentioned before. The next subsection is called arbitrary wrong correlation and 0 wrong coskewness. In this proposition, we use Gaussian copula and the marginals Fi in here to illustrate that the standardized wrong coskewness of x1, x2, and x3 is equal to 0 for any values of the wrong correlation of x1 and xj. Except the propositions, we use some examples to prove the second proposition. In the first example, we use the combinatoric copula. Then for any marginal distributions, the wrong coskewness is equal to 0, while the wrong correlations are all equal to 1. The second example uses the mixing copula from Rosgendorf and Oakland. And the mixing copula is a dependent structure such that the sum of ui equal to 3 over 2. When U1, U2, and U3 in these expressions, if we look at these expressions, we know that U1 plus U2 plus U3 is always 3 over 2 in here, like U plus this one and plus this one is 3 over 2. Then, under the mixing copula, the round coskewness is easily computed. It is equal to 0. But the round correlations are -1, 1, and -1, respectively. In the last example, we use independence copula. In this case, the round coskewness and the round correlations are all equal to 0. So these examples also proves our second proposition, like the coskewness can be 0. The coskewness is equal to 0 in this example, and in this example. But the round correlations can be 1, -1, 1, -1, or 0. In section 4, we deal with another type of coskewness that we introduced in the introduction. In the context of asset pricing and portfolio choice, the coskewness is typically defined as the following. The market gamma, or systematic skewness of the risky asset, also called the coskewness of X1 and X2, is defined as X1, X2 in here. So X1 can be the return of individual stock, and X2 can be the return of the market. In here, or in our point of view, X1 can be the loss of an insurance product, and X2 is the loss of the total insurance market. And similar definition for nu I and sigma I in here. Similar to section 2, we can construct a lemma in here. In this, we have the same assumption for the symmetric marginal distributions. But G2 in here is the distribution function of X2 minus mu2 square over sigma 2 square. So the maximum coskewness of X1 and X2, the S bar, is equal to this term, and it is attained by the copula of random vector U1 and U2 in here. Where the minimal coskewness S under bar equal to this term is attained by the copula of U1 and U2 in here. Figure 4 shows the support of the copulas that maximize and minimize the coskewness for the symmetric marginal distributions F2. So they are the plot of these two pair of equations. Okay, and the left panel in here is the plot for the maximizing copula, while the right panel in there is the plot for the minimizing case, minimized case. Then similarly, we define a two-dimensional mixture copula C lambda in here, applying the same principle that we did before. We know that the dependent structure of X1 and X2 is called a mixture copula C lambda when the bivariate random vector U1, U2 lambda is given as in here. Again, the bivariate random vector U1, U2 lambda is a linear combination of the bivariate random vector from the maximizing copula and the minimizing copula. So it's B times this term and plus 1 minus B times this term. Then under this two-dimensional setting, we use the mixture copula C lambda again and prove that the coskewness of X1 and X2 can take any values from the minimum coskewness S bar under bar to the maximum coskewness S bar, where the correlation coefficient of them is always equal to 0. This proves the first proposition. And the next, in the contrast, if we use the bivariate Gaussian random vector, the coskewness of x1 and x2 equals 0 for any possible values of the correlation of x1 and x2. Okay, then let me draw the conclusion here. In this talk, we provide some propositions and examples to illustrate that, in general, there is no link between the coskewness and the correlation, no matter the coskewness is 3-dimensional or 2-dimensional. And under the assumption of some specific models, for example, the normal marginal distributions and the mixture copula, or the Gaussian random vector, we observe that any possible values of coskewness, but 0 pairwise correlations of these variables. And we can have 0 coskewness and any level of correlation. Okay, then thank you for your attention.
Jeff, the international.
Anyone online have any questions? Please feel free to unmute yourself.
So maybe I'll start with a few questions on. I have, one main question and one out of curiosity. I'll start with out of curiosity. Why did you become interested in coskewness? Because it's not that I hear about it frequently.
Yeah.
I mean, for example, the fact that pairwise Pearson correlations being equal to 0 do not mean much for coskewness doesn't really surprise.
Yeah. Yes.
Why did you become interested in this problem?
Why we come to this 3-dimensional? Because we know that the efficient frontier, that's from Mark Weiss, they use only the correlation coefficient for the second dimension. But during these years, the literature found that only use the variance and the mean to define the risk is not enough. Then they extend this 3-dimensional coskewness and incorporate this coskewness to define the asset price in the literature. So we are much familiar with the correlation coefficients. Then we are curious about what are the mathematical properties of the coskewness in here, because it's a less well known. That's why we start this project about the coskewness.
I see. And in the context of portfolio theory, how do they interpret X3? I mean, I know that you're talking about the CAPM probably, right?
Yes.
So in the CAPM context, you have X1 being the rate of return, let's say, whatever asset, and then you have X2 being the rate of return of the market.
Yes.
What is X3 then here?
X3 then, as I talked in for this table. This type of coskewness in here, like we want to know, here is the market's return, for example, and then what is the relationship between the stock return and the square of the market's return.
Yeah, right. So in this case, your X3 is equal almost surely to X2.
Yeah.
So your X3 and X2 are the same random variables.
Yes.
But can you, in another formula that is more general, X1, X2, and X3, I suppose, are different, right?
Yeah, it's different. For that one, it's only in pure statistics, and we studied that one to add some contribution for the statistical reference. Yeah.
I see. Okay, then the follow-up question is this, because I was also thinking about portfolio theory.
Yeah.
Because this is definitely, I mean, the Pearson correlation is definitely connected to the beta, and everyone knows about beta, right? So it's very
Yes.
important.
Yeah.
What happens to your results if your part of, so x1 remains x1,
Yeah.
and x2 becomes a rank of x2. So you did, you went from,
Okay. Okay, I see.
and I'll tell you why I'm asking about that.
Okay.
Because there's something that's called Gini correlation
Mm-hmm.
that you didn't cover in here,
Yeah, no.
right? However, it's a very important measure of correlation introduced by Gini many years ago.
Mhm.
And then there are, of course, many, well, not many, but some works,
Mhm.
including Richard Zedekis wrote one and myself on Gini measures.
Measures.
And Gini, when we introduced Gini with Richard Zedekis, I don't remember when, we also sort of introduced a CAPM-like model for insurance.
Ah.
And then the beta there is different from the beta in finance because of the fact, exactly what I'm saying now. So the x1 in your language is x1.
Yeah.
But x2 can be an increasing function of a rank of x2.
Okay.
Can the map, what happens to the map? Can you?
Okay, I see. EU means if we use rank in here, actually it only changes the marginal distributions of this x2. In your language, you said it's the rank, right? But in our language, we can translate it to the marginal distribution of x2 is uniform. Yeah.
Correct. And then you take a function of that. So
Yeah.
in this case, you can think of this as your function being just x squared, right?
Yes.
So
X
imagine
squared.
a general W increasing, like x squared was increasing, so also increasing, but more general. And this, let's say, W of f of x2. Will it change the map dramatically?
W of what?
So here you have x2. So if we get, let's say this is 0, right? You have
Yes.
x2 squared.
Yeah.
This is like a square function of x2, right?
Yes.
So let's say that this, I don't know that this is square. Let's say this is just a general W function of x2 that increases.
Okay.
And I apply it to a rank, to the rank of x2. So W of f x2.
Okay.
So then this would be quite interesting because it will create then bounds on our Gini pricing.
Okay.
And then that just, again,
Okay.
out of curiosity, because you did either the usual case, right, or the rank case everywhere.
Yes. The rank case.
Based on what I saw. So your rank part of the talk is f1 x1, f2 x2,
Yeah.
f3 x3, right?
Yes. So if it's rank, the square means that it's the square of the uniform is between 0 to 1. It's still between 0
It doesn't
to
have to be
1.
square though. It can be any increasing function.
Any increasing function?
Well, you don't have to say now, but just.
Okay. Yeah, it's interesting, and we don't do this direction actually.
Yeah, this is why I'm sort of asking.
Yeah.
Okay.
Yeah, but we can find it in future to see. Okay.
Internet.
Any questions from the online audience? No, it was very clear.
It was in fact quite clear.
Yeah, it's true.
Awesome. Thank you very much. You're very concise and entertaining talk. I would say.
Okay, thank you.
No, from the point of probability, it's quite interesting, right? It's a interesting question.
Yes.
Or stops.
Okay.
Thank you.
Thank you so much for your.
I have one question, like, we considered that the customs and the correlations are not related,
Yeah.
but does that mean like we're not going to use it in the literature, or
No.
is there any way to use it?
No, I'm not means that you cannot use it in the literature because As you can see in today's presentation, we use different models and like we use different marginal distributions and copulas to get this result. I just want to give a suggestion that when you use the relationship between the coskewness and correlation, to be aware and be careful about your model that you use. So it can be a kind of model bias. It can be from your model. You don't find the relationship between them, or you find the relationship between them. So be careful to use the model and to choose the model in your paper and to get the result in here. Yeah.
I mean, like, I'm just an undergrad student, like, I don't have a background knowledge of those, but like, we can never be 100% clear. Thank you. I'm sorry.
Okay. Thank you. Also question.
Thank you.
Okay.
Thank you very much.
Thank you.